Quantum theory was developed to explain certain observations of matter and energy that could not be explained using classical mechanics. And here we'll show several examples, which we'll cover in more detail later on. So one example that's explained by quantum theory are the atomic spectra of hydrogen and other atoms. So in this emission spectrum, these are the wavelengths of light that are observed when an electron emits a photon of a specific wavelength. So you can see the atomic spectrum is discrete rather than continuous, because energy is quantized in quantum mechanics. And another example is black body radiation. So a black body emits electromagnetic radiation which depends on its temperature. And the photoelectric effect is where light behaves like a particle. So for example here, you have a metal bar subjected to electromagnetic radiation, and if the electron absorbs a certain wavelength of light, then a photoelectron is ejected from the surface of the bar. So quantum theory is necessary to describe the properties of matter at atomic and subatomic scales. And in quantum theory, fundamental particles can exhibit both particle-like and wave-like behavior. And this is called wave-particle duality, where, as we can see in the photoelectric effect, the electromagnetic radiation propagates like a wave, but transfers energy like a particle. And here is an example of the Bohr model, where fundamental particles like an electron can also behave like a wave. So because they're traveling very fast around the nucleus of the atom, then they create standing waves at different energy levels. And we'll go into this in more detail. So here we can see light going through a diffraction grating, and it exhibits wave-like behavior, being diffraction through the grating, and wave interference, which result in these different fringes displayed on the screen. And a similar thing happens to electrons. So experiments have been done where electron beams have been fired on crystals, and they've shown diffraction patterns. So diffraction is one of the behaviors of a wave. Light can be modeled as a wave and also as discrete particles. And these discrete particles are called photons. So for example, if we have a beam of light, we can visualize the photons in this beam as particles that exhibit wave-like behavior. So they're typically drawn in this manner. So Einstein used the idea from Planck that light came in individual quanta, or packets of energy, and he called these quanta photons. So the light behavior as a stream of photons is demonstrated by the photoelectric effect, which we'll look at in more detail. Now a photon is a massless, electrically neutral particle with the energy proportional to the photon's frequency. And the constant of proportionality is Planck's constant. So Planck's constant is very small, so it's around 6.626 by 10 to the minus 34 joule seconds. And recall from the relationship, being the wave speed is the wavelength by the frequency, where in this case we're looking at the speed of light, then we can also write the energy of a photon as Planck's constant by the speed of light on the wavelength of light. So photons travel in a straight line unless they interact with matter. And recall that the speed of light depends on the medium through which the light propagates, so the speed of a photon also depends on the medium. And the speed of all photons in free space or a vacuum is equal to the speed of light, which is around 3 by 10 to the 8 meters per second. So in general, the speed of photons in a given medium is inversely proportional to the index of refraction of that medium. So recall the relationship where the index of refraction was equal to the speed of light in a vacuum on the speed of light in a given medium, and then turning this around, we have the speed of light in a given medium being inversely proportional to the index of refraction, where the constant of proportionality is the speed of light in a vacuum. Particles have also been shown to demonstrate wave properties. So for example, in a variation of Young's double slit experiment, we may have an electron beam gun which fires electrons through two slits, and these electrons can be visualized as follows. So for example, they're particles that exhibit wave-like properties. So diffraction patterns will be observed on a screen, similar to what we saw with light. And these diffraction patterns are features of wave behavior. So wave interference causes these diffraction patterns. So essentially an electromagnetic wave can behave like a particle, as we saw, and a particle of matter, like an electron, can also behave like a wave. Now de Broglie hypothesized that a particle of mass m and speed v, so the particle is a linear momentum of mass by the velocity, has an associated wavelength, which was verified experimentally. So for example, by the Davison-Germer experiment. So this experiment showed a stream of electrons from an electron gun exhibited diffraction patterns when scattered by a surface of a crystal of nickel. So a wave model of matter is quantified by the de Broglie wavelength, which is inversely proportional to the momentum of the particle. Now it's important to note that photons, being light particles, have no mass, but they still have momentum. And this was explained by the energy-momentum relation in special relativity. So deriving this is beyond the scope of this course, but we'll just show it here for your information. So the squared energy is equal to the momentum by the speed of light squared, plus the rest mass of the particle by the square of the speed of light, and that's squared. So for a photon, it has no mass, so that gives the energy of a photon is the momentum by the speed of light, and as we've seen, the energy is equal to Planck's constant by the frequency of light, and the speed of light is the wavelength of light by the frequency of light. So therefore, substituting the energy into this second relation, we get the momentum by the speed of light is equal to Planck's constant by the frequency of light, and the frequency of light is the speed of light on the wavelength. So cancelling out the speed of light, you can turn this equation around to get this relationship. So this applies to light particles, or photons, and also fundamental particles like electrons, which were demonstrated to have wave-like properties. Now, quantum theory is necessary to describe systems where the de Broglie wavelength is comparable to the size of the system. So for example, if we consider a tennis ball, and that's struck at some velocity, so 200 kilometers an hour, or around 50 meters per second, and the mass of the ball is, say, 100 grams, or 0.1 kilo. So from that, we can calculate the momentum is equal to the mass by the velocity. So using Planck's constant, which is around 6.626 by 10 to the minus 34 joule seconds, and substituting for the momentum, you'll obtain a de Broglie wavelength is around 1.3 by 10 to the minus 34 meters. So although particles in motion describe wave characteristics and behave like they have a wavelength, macroscopic objects don't show noticeable wave-like behavior. So this de Broglie wavelength for our tennis ball is not noticeable at the macroscopic scale. And note that energy and momentum have discrete or quantized values. And the values for bound systems, like electrons bound to atoms, are described by quantum theory. Electrons are accelerated through a potential difference of 300 electron volts in a diffraction experiment, and we're asked to find the de Broglie wavelength of the electrons given Planck's constant, the mass of the electron, and the conversion of 1 electron volt to joules. Now 1 electron volt is equal to the kinetic energy acquired by an electron when it's accelerated through a potential difference of 1 volt. So therefore in our case, 300 electron volts is the kinetic energy acquired by our electron. And the de Broglie wavelength is Planck's constant on the momentum of the electron, and the momentum of the electron is the mass of the electron by the velocity, and the kinetic energy is 1/2 by the mass of the electron by the square of the speed. So therefore we can substitute for the speed, which is the momentum on the mass of the electron, and therefore one of the masses cancel, so we can write the momentum as the square root of 2 by the kinetic energy by the mass of the electron. So therefore we can compute the de Broglie wavelength as Planck's constant, which is 6.626 by 10 to the minus 34 joule seconds, and that's divided by the momentum of the electron, which is the square root of 2 by the kinetic energy, being 300 electron volts, which we can convert to joules. So we just multiply by 1.6 by 10 to the minus 19 joules per electron volt. And that's multiplied by the mass of the electron, which is 9.11 by 10 to the minus 31 kilos. So if we calculate this out, we get a wavelength of 7.1 by 10 to the minus 11 meters, which we can convert to nanometers. So 1 meter is 10 to the 9 nanometers, which gives 0.071 nanometers.